Okay, welcome everyone to today's PacTrans sponsored webinar titled UAS Applications in Transportation. My name is Cole Kopka. I'm the Assistant Director of PacTrans. We are the Region 10 University Transportation Center funded by the U.S. Department of Transportation. And today we are excited to have OSU Professor Chris Parrish join us. Chris recently completed a PacTrans funded project on this subject, and so we thought it pertinent to have him come on, talk a little bit about the work he's done, and have a little bit broader discussion about uncrewed aircraft vehicles, I believe, aircraft systems, sorry, uncrewed aircraft systems. So before I introduce our director, I just wanted to point out that we have the Q&A function available for you today. So at the bottom of your screen, you should see a little Q&A icon. You can click on that and you can put questions into that at any point during the presentation. We may not address them during the presentation, but we will definitely get to them at the end when we have some Q&A time. You'll also be able to see other people's questions. So if you see a question you really like, you can upvote it, and then we know which questions people most want to hear about. If we end up running short on time, we'll make sure to get to those first. And I think that's it. So without further ado, I would like to introduce our director, Professor Yinhai Wang, who will introduce today's speaker.
Hello, everyone. Welcome to the PacTrans webinar. Today, our speaker is Professor Chris Parrish. Before I introduce our speaker, I would like to briefly introduce the PacTrans research program. We normally fund two kinds of projects. One is so-called multi-institutional project. This requires multiple universities to work together. And Professor Parrish's presentation is about one of such projects. Another project we found is so-called small projects, and this could be just one university to work on the subject. And this is more on the exploration of new concepts and technology. Professor Parrish, his research focus is on uncrewed aircraft systems, Lidar, structure from motion, photogrammetry, hyperspectral imagery, and other emerging technologies for rapid acquisition of geospatial data. He has served as principal investigator for UAS-related research projects sponsored by multiple agencies, including PacTrans, Oregon DOT, Federal Highway, NOAA, and others. In 2018, Chris chaired the PacTrans-sponsored UAS in Transportation Research to Operations Expo. He holds a PhD in civil engineering with an emphasis in geospatial information engineering from the University of Wisconsin-Madison, and a master's degree in civil and coastal engineering from the University of Florida. He's the president-elect of the American Society of Photogrammetry and Remote Sensing, director of Oregon View, and the Coastal Processes lead for the NASA Surface Topography and the Vegetation Incubation Study. He also has experience with multiple agencies. He worked for NOAA, serving in multiple positions, including as a junior officer on the Hydrographic Survey Ship, Geodetic Liaison Officer in National Geodetic Survey, and lead physical scientist in NGS Remote Sensing Division. A very important award Professor Parrish received was the PacTrans Outstanding Researcher Award in 2020. He is very outstanding in not only research, but also societal services and other things. Now let's welcome Professor Parrish to start his webinar talk. Thank you.
Okay, thank you, Yinhai. Thank you, Cole. And for everyone else, sorry for the long introduction. I'll remember to send the short version of my bio next time. As Yinhai and Cole said, today I'll be talking about UAS applications in transportation based on some of our work up to this point, sponsored by PacTrans and others. Uh-oh, technical difficulties right off the start, right off the bat. Okay, here we go. So usually I don't do outlines for talks these days, but I thought I would today. And the reason I wanted to do this is I'm actually going to tie together a lot of different research that we did broadly under the theme of UAS applications in transportation. So I'll talk about structural inspections, in particular bridge inspections, Lidar UAS for traffic network monitoring, transportation-related surveying and mapping applications using UAS, Rockfall and Landslide site monitoring. And then kind of in tying these all together, I'll talk about some overarching benefits and also overarching challenges of using UAS for these transportation applications, particularly things focused on a state transportation agency, say, establishing an enterprise-level UAS program, including things related to organizational structure, standard operating procedures, pilot qualifications, safety plans, etc. I'll talk a little bit about driver distraction due to drones, and then conclude with a look at the future. One thing I wanted to say while I'm here on this slide is most of the work I'm going to be presenting today is work that my students and I led and were directly involved in. There's two exceptions: the Rockfall and Landslide site monitoring. That's work done by my colleague, Michael Olson here at OSU, and the driver distraction due to drones, work that I find just fascinating. That's another colleague and also the OSU Associate Director for PacTrans, David Hurwitz. So we'll talk about a bit about Michael and David's work as well. Okay, another thing a little bit different about how I organize this presentation today. Usually I leave the list of grants to the very end, but I wanted to bring it right up front in this presentation. And the reason why is this. Cole and Yinhai both mentioned that we did a multi-institution PacTrans project. This is the work I'm going to be presenting is actually a whole series of projects. And this is actually only a partial list. It doesn't include, for example, the projects of Michael and David that I mentioned just a second ago. But the main reason I wanted to move this up front is I wanted to talk about the top line here. So right after I started here at Oregon State University, I started in 2014. And I think this was maybe the second grant proposal that I submitted. It was with a colleague, Dan Gillens, who's now in NOAA NGS. So we were very fortunate to get at the time a PacTrans small project, which was one of the PacTrans research types that Yinhai mentioned. This was really fortuitous. Very appreciative of that. Not a large dollar amount, but it allowed us actually to jump into UAS. This was even before the Federal Aviation Administration released its Part 107, so we were operating under something called a COA at that time. But that initial small project then led directly into several follow-on phases of research. So about 6 years too late, maybe, I just wanted to say thank you to PacTrans. Since this is a PacTrans webinar, I wanted to express my appreciation for that, that first award all the way back in 2015 that kind of jump-started all of this work. And I would also encourage PacTrans to keep doing what it's doing and making those small projects available to new faculty. Okay, so back to these different applications of UAS. The first one that I want to talk about is use of UAS for structural inspections. And in particular, I'm going to focus here on bridge inspection. So a question you might have right off the bat is why use UAS for bridge inspection? UAS they're really just a tool in the toolbox. It's just one particular tool that bridge inspectors can use when they're doing an inspection. But I think it's a very important one. And the reason why is that it can reduce, I don't know if you all see my mouse pointer when I move my cursor around the screen, but it can reduce some of the things that you see here on kind of the right and lower part of the screen. Inspectors climbing on the bridge, use of bucket trucks, use of snooper cranes, lane closures. So UAS are not useful for every single bridge inspection. They're actually only useful on a fraction of bridges that a state transportation agency might inspect. But if you can reduce some amount of lane closures, traffic control, use of bucket trucks, snooper cranes, that can lead to potentially a huge cost savings over the course of a year, and potentially also some safety benefits as well. By the way, just very quickly, the particular bridge inspection that we see here, this was a great one. This is Winchester Bridge down near Roseburg, Oregon, and not the image showing the snooper crane down at the bottom, but the other three images, those were all taken on the same day. So if you see our inspection UAS there, we were acquiring data on the same day that an ODOT crew was there on a different span, physically climbing on the bridge and using the bucket truck. So when we first started this work, which I said was all the way back in 2015, which seems like quite a while ago now, one of the first things we did is we looked at what are the requirements of a drone, of an inspection aircraft for doing bridge inspection type work. The particular aircraft that we see here is actually now obsolete. You can't even buy this anymore. But a lot of the characteristics of this one are still remain today, characteristics that you would want to see in an inspection aircraft. And I'll talk about them briefly. One of them is that you really want to use multi-rotor aircraft as opposed to fixed wing aircraft or gliders, things that operate more like a conventional airplane. Those ones tend to be good for acquiring data over large areas efficiently. But if you want to be able to hover in place up near the bridge and have the inspector zoom in on a particular element and capture, look at that from slightly different angles, maybe by tilting the camera, you really want an aircraft that can hover. Also, vertical takeoff and landing is important. A lot of times in doing bridge inspections, you're operating in tight spaces, so you don't have a huge amount of room to take off and land. So things like the quadcopter here, shown here, or other multi-rotor are really helpful. The second thing, obstacle avoidance. The main goal here is you really just don't want to crash into the thing you're trying to inspect, right? You don't want to fly the drone into the bridge that you're inspecting. Whenever I say that, people laugh. It sounds so obvious. It's kind of like, duh, right? You don't want to crash into the bridge you're trying to inspect, but that can actually be tricky in practice. A couple things that make this challenging are flying these kind of small UAS right up next to a large structure. Depth perception can become very tricky. So if you're standing down on the ground, it can be very difficult to see if you're 2 feet versus 20 feet away from that structure, unless you're using first-person view or something like that. So, oh, and then the other thing is there can also be gusty winds, a lot of turbulence up near the structures. At times, those can try to push the aircraft towards the structure. So having obstacle avoidance through navigational cameras, sonar, Lidar, radar, that's super helpful. And then shown over there on the right, another thing you really want in a structural inspection aircraft is being able to tilt that camera head. So everything from being able to tilt the camera straight down for more like mapping missions, to straight ahead for inspecting a structure from the side, to being able to point it up so that you could actually fly that remote aircraft, for example, under a bridge deck for looking up at the floor system. And then really quickly, thermal imagery, thermal IR, that can be helpful. I've got to say, we didn't use it. This particular aircraft did have a built-in thermal camera. We didn't use it too much, but other researchers have shown that that can be beneficial, for example, for detecting delamination in bridge decks. So this is a quick look at some of the bridges that we inspected with the UAS during our first couple projects. Independence Bridge, that was the first one that we started with. I don't know why we picked such a hard one to start with. Independence Bridge is a fracture critical bridge, also very large, a difficult place to start, but nevertheless, that was the first one we did. We did a couple bridges in Central Oregon, Crooked River Bridge and Mill Creek Bridge. Crooked River Bridge is actually currently a pedestrian bridge only. They built a new bridge just to the east of the old bridge. That was really helpful because based on ODOT's rules or restrictions for us, they didn't want us flying up above the bridge deck. And the reason for that is they didn't want a drone suddenly popping up above the bridge deck and potentially startling a driver, which is certainly a real concern and something I'll come back to when I mention at the end David Hurwitz's driver distraction due to drones work. But the fact that it was a pedestrian bridge, we could do some additional things there. From there, we went to Mill Creek Bridge, St. John's, beautiful steel suspension bridge up in the Portland area, and then Winchester, the one I already mentioned, down in Roseburg. Okay, I've given other presentations where I've shown examples of the imagery that we collected. I'm just going to go through these really quickly. We collected something like 4,000 or more than 4,000 images in these projects. I'll just show a quick few examples, things that the inspectors flagged for us as being of interest. So cracking in the concrete railing, this is Independence Bridge, the missing bolt head that had been painted over here. Looking at rocker bearing alignment. So is it vertical? Is it rocked over? Looking at the pin connection in the lower chord there. Oh, and then this one was kind of interesting. This one is Mill Creek Bridge. So here we see no evidence of movement of the joint that's in the upper chord, and then going down to the lower chord there, you do see evidence of movement of the joint in terms of both the rust and the location of the pin. Winchester Bridge, this was the first one where we actually flew under the bridge deck looking up. So really beneficial to be able to do that in these bridge inspections. Also, frankly, a bit scary being able to do this. The big issue when you fly the aircraft under the bridge deck is you tend to lose GPS or GNSS, Global Navigation Satellite System signals. And one of the issues with that is, well, it's making your navigation much less accurate. But the other thing that happens is when those GPS signals are coming in and out, if you lose them and then suddenly reacquire them, that can actually cause the aircraft to jump. It kind of, the way I envision it is it suddenly realizes that it's over here when it should be over here. And so all of a sudden it will just jump somewhere else. And obviously that can be a bit scary when that happens. So what we ended up doing is recommending to just turn the GPS off on the aircraft when you're flying under the bridge deck. And then St. John's Bridge, again, looking at a rocker bearing, looking at some spall there, debris, and using the lessons learned from that. Winchester Bridge, the St. John's Bridge was another one where we got a little bit more confident and were able to do more work flying under the bridge deck. Okay, so for the most part in those structural inspections, when we were working with the bridge inspectors, they, for the most part, had in mind to use the UAS kind of like a flying pair of binoculars. Basically, what they wanted to do was be able to take the aircraft up to a certain height, zoom in on a specific element, and kind of do the things that they could do with a high power pair of binocs. Completely fine way to use the UAS. But one of the things we wanted to do in this project is actually document going above and beyond that. So for this Crooked River Bridge, which, as I mentioned, is a pedestrian-only bridge at this point, we were able to do this mapping mission, basically flying a grid pattern both up above the bridge deck and then along the side, going back and forth like you see up there in the upper right. From there, we could take that imagery and put it into a new form of photogrammetric software called Structure for Motion Photogrammetry. Do this 3D reconstruction and then generate point clouds. And let me actually show you what that looks like. So if this is going to work, this is actually a video. So we've got a 3D point cloud of this Crooked River Bridge that was created from that 3D reconstruction and the Structure for Motion Photogrammetry software. Something I'll say about this is it might look like a solid 3D object. It's not. What we're seeing is actually comprised of millions, maybe tens or even hundreds of millions of individual points, each with XYZ spatial coordinates. I think you'll see this a little bit better as the video kind of turns here. Hopefully you can see that each one of those things is an individual point in space. I'll give this a second to continue just because I think it's pretty cool. Former student Matt Jones created that. Okay, I'll keep going. Whoops. So what is the power of this? Well, having that kind of georeferencing where you've got that point cloud where each point has accurate 3D spatial coordinates, this gives you a way to link the 3D real world, this 3D point cloud, and then the 2D imagery. So if the inspector has a particular element they're interested in looking at, a particular pin connection, and they know where this is in the real world, or they can find it in this point cloud, it's as simple as being able to click on that, and then you can bring up every single image, every single UAS image that saw that that particular element or feature, whatever it is the inspector is interested in looking at. If the UAS acquired imagery of it from multiple different angles, flying heights, viewing geometries, whatever, you can pop up all those images. So the final thing that we did in that bridge inspection work is we did a cost benefit analysis. And going in, I've got to say, this was the part of this study that I was initially most concerned about because I will freely admit I am not an economist. So we tried to be very conservative in how we did these cost estimates. Basically what we did is we took a spreadsheet that we were given of all the bridges that ODOT inspects in a given year. And we looked at what percentage of them would be suitable for a UAS bridge inspection. And there's a lot of reasons why a particular bridge would not be suitable for UAS. For one thing, it might just be too small. I mean, maybe a UAS could fly the bridge, but if it's small enough that an inspector could just see everything that they needed to see just by walking under the bridge or along the bridge deck, then there really wouldn't be a need for a UAS. In this analysis, we also threw out everything that was in controlled airspace or other than Class G airspace. We didn't necessarily need to do that because these days it's getting easier and easier to request airspace authorizations with things like FAA LANCE. But for this study, if it was not in Class G airspace, we threw it out of the analysis. If it had overhanging vegetation, cables, anything that was going to potentially be dangerous to the UAS, we threw it out. And that left something like 1/6 of bridges were potentially suitable for UAS inspection. And then we estimated if we could do a 20% cost savings in terms of equipment rental and renting super cranes, bucket trucks, and lane closures. We estimated the cost savings for that. Basically, we took the average cost savings per suitable bridge times the number of bridges per year times the percentage of bridges suitable for UAS, and that came out with over $1 million. And I was kind of concerned, again, presenting this to ODOT. I didn't know if they were going to come back and say, well, you know, you're not an economist and you forgot X, Y, and Z. But they seem to think that was fairly realistic, and since then, other studies have actually shown potentially even greater cost savings for doing this kind of thing. You do need to also figure in addition to the benefits, you need to factor in the costs of running a UAS program. But in any case, we came out with something like a benefit cost ratio of 9. Okay, moving on. This was the project that Ninhai mentioned right at the beginning. So this was our multi-institution project with University of Idaho. What we were doing here, if you look at this image in the lower right, this is the vision, right? So basically the idea here is you've got a fleet of LiDAR-equipped UAS that are monitoring a traffic network. And so you've got the UAS kind of flying around, they're communicating with each other, they're communicating with these hubs, which in turn are relaying information to managers, to transportation agencies, potentially to vehicles, things related to emergency response, congestion, clearance, accidents. So you might look at this and say, well, Chris, this is kind of pie in the sky. It seems kind of out there. I actually agree with that. I think this is kind of a long range vision. We're not really there yet. But I would also say that a lot of the current challenges in achieving this are actually not technological. They're a lot on the regulatory side. But anyway, our goal in this project was kind of to see how far we can get in this direction, test what's currently feasible. So one of the first things we needed to do for this is equip a UAS with LiDAR so we can test this LiDAR, light detection and ranging. There's a, hopefully people are somewhat familiar with this little cartoon over on the right. So you're transmitting laser pulses, measuring the round trip travel time, using that to calculate a range, combining that with GPS and an inertial navigation system and scan angle data to get XYZ coordinates and be able to generate point clouds similar to the one that I showed for a Crooked River bridge. Why use LiDAR with this? As I already showed, you can do the same thing using imagery. That was the Crooked River bridge example. The reason why LiDAR is so critical here is structure for motion photogrammetry using the imagery is just too slow. It processes for hours, depending on the size of the project. It can process overnight. Meanwhile, Lidar can achieve better than one-to-one acquisition to processing ratios. So if you need real-time coordinates of things for this traffic network monitoring, Lidar is kind of the way to go. So we equipped our Lidar UAS. We did a number of test flights, starting with this highly controlled test environment on the OSU campus up in the upper right. From there, we moved on to a construction site, the Newburgh-Dundee bypass construction site. We flew this right before the bypass was open to the public. And then the final test that we did was up at the University of Washington campus, flying along this or near this traffic intersection. All the flights were conducted under FAA Part 107. Okay, if this works, I'm actually going to jump, bring this up in my browser. This is just a little video. So this was flying that, when it starts, you should see the aircraft take off over here. So here's the aircraft. This is actually drone-to-drone footage. So you can see the Lidar aircraft flying alongside the roadway. If it looks like the aircraft is actually over the roadway, that's just a matter of perspective. I promise it's not. We followed David Hurwitz's recommendations in the driver distraction due to drone study that I'll talk about later. But anyway, flying along. Oh, one question you might ask in looking at this is, does the relative motion between the aircraft and the vehicles create distortions in the point cloud? The answer is yes, it does. So that's something that we had to take account of. All right, let me lower that and go back to PowerPoint. Okay, so just a second. As I mentioned, this was a multi-institution project. Our project partners were at University of Idaho. And the part of this that they led that was kind of cool was coding up this machine learning algorithm for auto detection of vehicles in the scene. And the goal here was to try to make this efficient enough that it could run in real time. So they're doing this sort of parallelization of the scanning and then the data processing. Here's a template of a vehicle. So this was kind of a template matching approach, but utilizing machine learning. Just really quickly summarizing their results from that. And I did sort of pick out the best set of results here, but they were able to achieve up to a 100% detection rate with a 25% false alarm rate by carefully choosing the settings in their processing algorithm. The most important thing about this, though, is this is all, again, done in a way that it's designed to be efficient enough that you can run this in real time on the type of processor that you could put on a UAS. Another thing that we did in this project, let's see if this one runs. Oh, there it goes. So here we've got a, over on the left, that's just a static image of the setup that we had. So this is over an intersection, 14th Street and Monroe Avenue, just right across from my office, actually. Looking over this intersection and doing the scan as vehicles were passing through the intersection. I don't know how well you can see it. With this particular scanner with 16 beams, the spacing between the beams kind of gets larger as you get further away from the scanner. But hopefully you can see, you know, as the bus, for example, goes through the intersection, you can detect it there. This leads to a question. So do you actually need UAS for this type of traffic network monitoring with these sensors? And I think that's a really good question. This is just my personal thought, but I feel that the future of all of this is that if we are able to get this type of traffic network monitoring system, it's going to be probably a combination of fixed mounted sensors that are on poles or signs or overpasses or something like that, along with UAS. The thing that the UAS brings is if you're trying to go inspect an accident site or something like that, and it happens to be in between these fixed mounted sensors, the fixed mounted sensors just don't have that ability to move. But I think that ideally, you know, in the future, if we can get there with regulations and other things, this combination of the fixed mounted sensors and then those mounted on UAS is probably the most powerful solution. Okay. Another great thing that PacTrans does, by the way, is it requires all PIs to make their data available. So if anybody is interested in the data from that traffic network monitoring project with Lidar UAS, we've got the point clouds and LAS and ASCII formats, metadata, our final report, our video, all of that is available for download. Next set of applications, near and dear to my heart, surveying and mapping. So there are a lot of transportation related surveying and mapping type applications that UAS can be great for. The big focus here is, unlike in other applications where you just need kind of quote unquote pretty pictures or nice imagery to analyze visually, in surveying and mapping, we really care a lot about things like spatial accuracy, spatial resolution, datums, coordinate systems, map projections, units, having good survey control. So what do? Well, first of all, let me back up a second. Two ways that we can collect surveying and mapping data using UAS, two technologies. I've already kind of mentioned them, but I'm going to go into a bit more detail here. So we've got imagery, just kind of like, I don't know where my cell phone went, you know, red, green, blue imagery, like the kind that I could acquire with my phone, maybe a little bit better camera, hopefully a much better lens. But flying over the area, collecting imagery, putting that in the photogrammetric software, creating point clouds like the one of Crooked River that I showed earlier. And then on the other hand, airborne LiDAR. So airborne LiDAR is kind of an animation here, again, using laser ranges. Both of these have pluses and minuses. There are trade-offs involved. So imagery, pretty easy to collect, relatively inexpensive. You're really reliant on illumination conditions. LiDAR, in theory, you can collect at night, at least if that's allowed under the regs. And by the way, the FAA has recently released some changes that are making it slightly easier to do nighttime operations. But anyway, active technology is using its own source of electromagnetic energy, so you're not reliant on the sun. You do need bigger, heavier systems. I'll kind of show you why. First of all, just an example, a couple different examples of LiDAR UAS over on the right, and then UAS equipped for acquiring imagery on the left. Kind of deeper than I want to go, but I'll just talk about this quickly. So actually I teach a class in photogrammetry. We talked a lot about this back in the winter term in my photogrammetry class. How does this even work when you're doing the 3D point cloud generation from imagery? Well, it works like this. You do the UAS flights, you've got to have a lot of overlap. So each consecutive pair of images has to overlap by quite a bit, 75% or more, the previous image. And then for flight strips, you need overlap side to side too. You throw this into software, it creates feature matches. You also put in ground surveyed ground control points, camera parameters. It goes into a big least squares adjustment. You get out a sparse point cloud. It goes through another type of software called multi-view stereo. You get a dense point cloud like the one for Crooked River Bridge that I showed. And you can also do other products, ortho images, which are images that have had the distortions removed and can be used like a map. Usually they're georeferenced, so every pixel has precise spatial coordinates. You can output digital elevation models, 3D meshes, etc. On the other hand, LiDAR, I already showed that cartoon of kind of how LiDAR works with combining the ranges with the GPS and the scan angles to get point clouds. The main point I want to make here, though, is LiDAR has greater requirements in terms of to be able to get those accurate spatial coordinates. First of all, you need more hardware on the aircraft. You need something called direct georeferencing, or GNS, Global Navigation Satellite System, aided inertial navigation system. I won't go in detail here what that means, but suffice to say, you've got another piece of equipment that's got to be mounted on your UAS. You've got to process the trajectory. You need good GPS for this. So I'm guessing a lot of people have heard of RTK, real-time kinematic, or PPK, post-process kinematic. You might have heard of PPP, kind of new and emerging, precise point positioning. So these are kind of things that people, I don't necessarily like this term because it's a bit vague, but people will refer to this as quote unquote survey grade GPS or GNSS, where you're getting down to accuracies on the order of a few centimeters. You really need this for doing UAS-based LiDAR. So this leads into a great study that I'm just going to show really quickly. This was done by a former grad student named Chase Simpson, and Chase is now actually an instructor of geomatics at OSU in the School of Civil and Construction Engineering, and really glad to have Chase as a colleague now. But this was back in his grad student days. He came to me with this project he wanted to do, and he said it was going to answer this question of which is better, UAS Lidar or UAS Imagery and the structure for motion photogrammetry. I love this topic right from the beginning, but I remember saying to Chase, I said, Chase, this is kind of unanswerable. Anytime you get one of these questions like which is better, technology A or technology B, the answer always comes out to be it depends, right? And Chase said, oh yeah, I know that, but I feel like we can do a good study and evaluate and compare these across multiple dimensions: cost, accuracy, complexity, learning curve, etc. And I said, okay, it sounds great, go for it. So Chase did this fantastic study and survey. He did this really accurate control survey. This is up in the Port of Skamania in Stevenson, Washington, along the Columbia River. So you can see his control survey. He acquired data with multiple different UAS and also terrestrial 3D laser scanning on different surface types. So sparse grass, concrete, asphalt, all these different surface types. Okay, I'm trying to advance the slides. Okay, so some of Chase's findings. One of them that's really interesting is looking at achievable point densities between those technologies. With the LiDAR, we were getting point densities of around 50 points per square meter, which sounds pretty good, except when you look at what you can get from the imagery, it is over 5,500 points per square meter. Also, as I mentioned, the LiDAR, greater complexity, greater cost, a lot heavier, steeper learning curve. You can see kind of this table of trade-offs. I'm really summarizing a ton of great work that Chase did very, very quickly. But basically the conclusion that Chase came to is for a lot of surveying and mapping type applications with UAS, including those that are of interest to transportation agencies, the imagery-based approach, the UAS imagery and the structure for motion photogrammetry tend to be kind of the method of choice. You might want to consider that as kind of the default. It's got low cost, easy implementation, and comparable accuracies. That said, and this is really interesting, one of Chase's main findings is that there are certain cases when the imagery solution is not preferred, and when you really want to go to UAS-based LiDAR. What are those situations? One is when you have this uniform or homogeneous surface texture. Another is when you've got canopy vegetation and you need to, quote unquote, penetrate through the canopy to get down to the surface. LiDAR tends to be good at that. Penetration is kind of it's the wrong word. It's not the laser light is actually going through a tree leaf or a branch or something like that. But if just part of that laser light can make it through to the ground below, then you tend to be able to get ground elevations. Poor illumination and large number of vertical obstructions, trees, buildings. Those are all cases when you might want to use LiDAR. One of the real areas where the SFM struggled a bit is, as I said, on these sort of uniform, homogeneous surface types like the asphalt. So here, this might be a lot to look at, but we're looking at 3 different surfaces: asphalt, bare earth, and grass. The bare earth and grass have more texture to them. And so if you look at all the data, including in light green, the structure for motion photogrammetry, and then the LiDAR and the ground truth, for the bare earth and the grass, everything agrees pretty well. But if you look at the asphalt, that imagery-based approach, there's a lot of scatter to it. It really just didn't do as well. And then the situation in which the UAS imagery and photogrammetric approach really struggles is when you have a combination of things. If you have a combination of poor illumination, like in this tree shadow, and then you've also got the low surface texture from the asphalt there, you really see that large scatter if I don't know how well that stands out, but if you can see the light green points in that lower right diagram, really a lot of scatter. If you even add a little bit of surface texture like on the right, all of a sudden it gets a lot better. So can we quantify this? The answer is yes, we can. And this leads to the work of another fantastic former graduate student, Richie Slocum, who got his PhD about a year ago. Richie built this amazing thing, which we ended up calling simUAS. What is this? Well, I think this is just super cool, and I don't take any credit for this. This was Richie's idea from the beginning. But this uses computer graphics software, so CGI software, similar to what's used, for example, in making animated films, to create this virtual scene. So you take a digital elevation model, any kind of topography you want, you drape whatever texture you want over it. You can change the illumination using custom scripts that Richie wrote. You can also add camera lens distortions and other types of effects. But then you create all these individual camera stations. So the little yellow dots up there in the upper left, those represent 3D locations from which a simulated image is taken. And then you generate this database of imagery. And the really cool thing about this is it's so photorealistic, you as the human operator would be hard pressed to look at this and say, this was simulated versus this was acquired from an actual UAS flying over the scene. Even more importantly, the computer also doesn't know the difference. So the computer software, when you put this into the structure for motion photogrammetry software, it does not know that this set of images was created through the synthetic process rather than through an actual drone flying over the scene, collecting imagery. So you put it in the SFM, you generate the point cloud, you generate the ortho image, and then you can compare it to the original scene. And every single point in that original scene is basically a ground truth point because it's simulated, so you know exactly where it is. So this is great for accuracy assessments. It eliminates all the uncontrolled variables, wind conditions, changing illumination, and things that you get in an actual empirical study. So super cool. Here's just an example. In this case, Richie placed the simulated block in the scene, and then you can see the points from the different SFM reconstructions and basically see how accurate that is. So in another project, I've got the NOAA logo here. This is a project that we're currently doing with NOAA, but we're looking at the vertical uncertainty of those structure from motion point clouds as a function of the drone's GPS, basically. So really a cool thing that we can do. And we're currently looking at validating that through some field surveys. Okay, I think this is actually the final application that I was going to mention, and this is back to one that is not my work. This is work of my colleague Mike Olson and another colleague Ben Lashinsky and a former student Ben Babel. So they've done a lot of work in looking at UAS for rockfall and landslide site monitoring using both UAS and imagery-based approaches like I just talked about. This is the Spangler landslide. It's part of the Molina landslide complex about 22 miles southeast of Portland. A large landslide complex that Highway 213 passes through, and that's caused a lot of damage to the highway at various times. So basically and then also rockfall site monitoring. So Mike goes up every year to Alaska and does data collection on these rockfall sites. I got to go up there once, a lot of fun. Some of the things that they found, so UAS Lidar can be a cost-effective, efficient method of repeat mapping and monitoring change. This type of thing can provide input for models, failure modeling, analysis, and prediction, looking at landslide kinematics. So with all of those applications in mind that I just went through relatively quickly, I apologize. What can we say? What are the benefits of UAS for transportation? I would say there are a lot, and they generally fall into these broad categories: cost, efficiency, safety, things that we saw in the bridge inspection and the rockfall site monitoring, multi-use of data, by which I mean the ability to collect data for one specific project, but then turn around and use it for a whole host of other things, some of which might not have even been envisioned when the data were first acquired. We've shown that UAS are already efficient for bridge inspections. And by the way, this is kind of already operational. And I don't take I don't want to overstate our credit in this. A lot of other groups have done research and UAS for bridge inspection, and this is slowly starting to be more and more an operational capability. Other transportation-related structural inspections, I didn't really mention this, but at the time we did that follow-on to the first PacTrans project with ODOT wanted us to look at communication towers as well, so we did that. I talked about the landslide and rock slope monitoring in Mike Olson's work. Again, just a whole host of transportation-related surveying and mapping type projects. Transportation construction site monitoring, yet another colleague that I haven't mentioned yet, Yelda Turkin, is using UAS for construction site monitoring. And things that are coming in the future, traffic network monitoring, infrastructure monitoring. Okay, challenges though. There are quite a few challenges as well. So for a large state transportation agency trying to operationalize UAS, things like pilot qualifications, proficiency, safety for both the UAS flight crew, but also for motorists. Regulatory issues beyond visual line of sight, airspace, night operations. Just back in April, the FAA released new regulations that facilitate a bit things like flights over people and over moving vehicles and nighttime operations beyond visual line of sight. So as of right now, you need to be able to keep the UAS in unaided line of sight. That's one that a lot of people are hoping is eased up on a bit. IT, collecting huge volumes of data. We collected literally terabytes of data during that bridge inspection work. Along with that, the idea of all the processing that needs to go on, just IT security, other IT related issues. Let me quickly talk about this one though, the driver distraction due to drones. Again, this is David Hurwitz's work. And I wanted to mention it because in the past, when I've given presentations on this research, even if I just barely mention David Hurwitz's driver distraction due to drones, when I get to the Q&A session, all of the questions seem to be on David's work. We'll see if that's the case today as well. But I just find this fascinating. So here's a little cartoon by an Alaska task force about the potential for drivers to be distracted due to UAS. And it was a 2017 survey of transportation and law enforcement officials in which 21% reported UAS operations near roadways and 92% saw driver distraction as a potential hazard. So what David and his students have done is to be able to investigate this rigorously using their driving simulator. By the way, I don't know if David is on the line today. He might wince as I try to explain some of his research. If I get anything wrong, maybe he'll be able to correct us after the fact. But he's got this driving simulator, so a 2009 Ford that the driver sits in there. And then what makes this really rigorous and quantifiable is they can actually track the eye movements of the driver. And so this isn't just subjective analysis where they ask the driver after the fact, hey, did you see the drone? They can track it. So they can put the simulated drone in different environments, or urban and rural. They can look at the total fixation duration and dwell duration. So they did this with a bunch of different subjects. Oh, and by the way, the reason this is important is that studies have shown that glances of greater than 2 seconds away from the road nearly double the near crash or crash risk. So some of the findings from the work that David and his students have done, UAS operations near the roadway do induce quantifiable glances away from the roadway. Recommendations prohibit UAS operations within 25 feet of the roadway. That was how we knew how far back to stay from the roadway in some of those Lidar UAS flights that I showed earlier. Consider more stringent restrictions in rural jurisdictions, possibly allow for exemptions for limited activities such as emergency response. And then as a follow-on to that, David and his research group has looked at whether UAS distractions can be mitigated through signage. And so they've looked at different sign designs, including the wording, the pictorial elements of the signs. So they've looked at these different sign alternatives and come up with the 3 best performing. Before this comes up in the Q&A, I'm sure somebody's going to ask me which ones were the 3 best. I meant to look that up before the presentation. I don't know, but if David's on, he can tell us which 3 were the best. Okay, kind of in wrapping up here. I know I covered a lot of ground, but Best practices, recommendations stemming from this whole range of different projects that we've done in looking at UAS for transportation applications. One is for a state agency getting into work with UAS. We strongly recommend establishing a formal UAS program with standard operating procedures to, among other things, codify operational decisions. That was something that we found early on. You kind of don't want your flight crews getting out into the field, doing a bridge inspection, for example, and looking at each other and saying, well, it's kind of windy. Is it too windy? Can we operate today? Or do we call it? I mean, those kind of things, like what's the max wind speed? Those are all kinds of, and there are a ton of others. That was just one example, but things that you want to document and have codified ahead of time. So you're not requiring people to make challenging safety related decisions in the field. To have a defined organizational structure with roles and responsibilities, safety plan templates, airspace authorization procedures, pilot qualifications. A lot of groups are going above and beyond. The FAA Part 107 qualification is usually sort of the minimum standard, but then a lot of organizations are now doing additional pilot training and having additional pilot currency requirements. In the field, you want to use a visual observer. That's actually not required strictly under Part 107. But for example, if you're doing a bridge inspection with the UAS and the operator is using first-person view, where they're using imagery from the perspective of the UAS to kind of maintain that safe standoff distance, the FAA in that case requires that you have a visual observer who's has unaided visual line of sight to the UAS. Takeoff and landing zone free of personnel and equipment, use anti-collision lighting. That actually can really help in actually seeing the UAS. For a visual observer whose only job is to keep track of that UAS, it can disappear on you pretty quickly. You know, up against a rock wall, up against a large structure. So that can kind of help using the geofence. No firmware updates in the field. So if your UAS wants you to do a firmware update and you're about to take off and inspect a large bridge or something like that, hold off. Perform basic level of QA/QC in the field. ODOT is one agency that has done something like this. I don't want to give ourselves too much credit. ODOT has a great program, and I think they would have been able to do all of this, frankly, probably without our help. But I'm pleased to say that I think some of the recommendations that we had from some of these phases of our work actually did make it into ODOT's operational manual and their operational UAS program. Looking ahead, what's next? In terms of the aircraft themselves, things like these hybrid aircraft that can do vertical takeoff and landing, but then convert to a fixed wing aircraft. A colleague of mine, Mike Sterk, who's at Texas A&M Corpus Christi, we've got a project with him where they're flying this aircraft. Really interested in that. Things like better direct georeferencing, as I mentioned earlier, that GNSS-aided inertial navigation system on the drone. Obstacle avoidance, I see a lot of machine learning and computer vision coming in to do more and more with things like automated obstacle avoidance, new sensor types, hyperspectral imagery, autonomous flight in areas where you're not getting good GNSS, like under the bridge deck. And then the biggest one, I really see a lot of work coming in machine learning, artificial intelligence, and taking these huge volumes of raw data and turning that into information. And being able to, this is an image from a colleague, Chris Higgins here at OSU, being able to automatically detect defects, to be able to automatically detect change over time. That is going to be huge as we collect just larger and larger volumes of imagery. There's no way a transportation agency, I don't think, could realistically pay for a whole team of human analysts to sit there and one by one look through these huge imagery databases. This has got to be automated. So those are things that I see are coming. Okay, references. I believe Cole and Yinhai said that these slides will be available. I don't expect you to read all of this, but just to let you know that a large number of publications have come out of this work, and I'd be more than happy to follow up with anyone who wanted more information on any one of these studies. And with that, I do apologize for covering so much information so quickly, but hopefully that was useful. And the time remaining, if it's okay with Cole and Yinhai, I'll be happy to answer any questions.
Yeah, that was great, Chris. That was a lot. Thanks for all the plugs for PacTrans, and we're certainly proud of the way that the our resources have been leveraged and kind of what that's all led to. So this is fantastic. As Chris just mentioned, this is being recorded. We will make this available. So if you want to go back and review, or if there are others who you think might be interested that you want to share, this can be found on the PacTrans YouTube channel. We'll also post it on our website. But yeah, so we have about 5 minutes for question and answer. So please feel free to click that Q&A icon at the bottom and submit your questions. We did have one question come in during the bridge inspection portion of your presentation. And it basically asks what the reason was for selecting a vehicle with single pilot payload operator as opposed to a two-person crew.
Yeah, I was just reading that question. That's a great question. Thanks for asking that. We kind of sort of did end up going with this general approach because a lot of times the person that was actually flying that may or may not have been the pilot in command. So, you know, FAA Part 107, you need a PIC. That doesn't necessarily have to be the person that's actually operating the sticks, but whether they were or weren't, the person operating the sticks often was looking at first person view and not looking up and seeing the aircraft. So when you do that, I may have mentioned this briefly, but when you do that, the FAA actually requires that you have a second person that's the visual observer that has unaided, you know, line of sight to the UAS. So we did find that that was generally the best mode of operating, and the reason for that was, again, when you're doing this inspection of a large structure, that depth perception as that remote aircraft gets up close to that structure can just be so tough. So it can actually be much easier for the person flying, for the person operating the sticks, to be looking at the first person video. That said, there's a second part of this question that I think is great. It talks about the helmet and the glasses. And I don't know how many people have watched drone racing on TV. I've never done that, but occasionally I'll turn that on TV, and it just looks fascinating. I think I would be absolutely terrible at it. Maybe some of my students would be good, but I do like that setup with you know, like the glasses. I think that if we could get some of that out of the drone racing world and into the UAS inspection world, that could be a big benefit.
Yeah, I wonder too if that would minimize any potential distraction for the operator, because the entirety of their vision would be what they're seeing through the drone. Yeah, interesting.
So Chris, this is very interesting. While we don't see another question, I want to take the opportunity to ask my question. So sure. You showcased a lot of very interesting applications. To me, I think the benefit to cost ratio is very high. But what's your concerns or recommendations about the potential barrier that you could see to really try to implement the UAS-based solutions? What is our next step?
Oh, so barriers and next steps for implementing this operationally. Mm-hmm. So I think it clearly can be done because, again, ODOT has implemented their UAS program. I've recently given a presentation to Caltrans, who is doing a lot in UAS. Utah DOT is another state agency doing a lot with UAS, and a lot more. Those are just the ones that I've interacted with. I think, again, big challenges, kind of some of those that I alluded to in terms of, you know, just setting up this organizational structure. It's something new, right? And the volumes of data acquired, at least for agencies that aren't already in the world of doing things with mobile Lidar or other types of data collection that just collect terabytes of data very, very quickly, dealing with the data, you know, from the IT side of things, and then being able to efficiently process that data. It doesn't do anyone any good if you're collecting these huge databases of imagery, but it just sits there untouched. And so that's really where the area that I see, because I just don't, to me, it doesn't seem realistic to think that these transportation agencies are going to hire whole divisions of people to come in and do manual analysis. I really see that whole machine learning AI piece as being a big next step to take a lot of the things that we've talked about and make it more of a reality.
So do you see any like constraints from like the regulation perspective about using UAS?
Yeah.
Because if we demonstrate the technology, if there are some kind of procedure obstacles there, we could probably outreach to see how we can lift that.
Yeah, that's a great question too. I think things are moving in the right direction. In 2016, when FAA released Part 107, that was a huge step forward. Before that, we were actually really fortunate at OSU. We were one of the few universities in the entire nation that had a centralized UAS program set up where we could receive certificates of authorization, COAs, to be able to go fly UAS. But for other people, there were just a ton of hoops to jump through to do that. When Part 107 was released in 2016, the whole goal was to open up the national airspace to UAS, but there continue to be constraints that are really difficult. One of them that is a huge constraint in transportation is not being able to fly over moving vehicles. Obviously, you know, that's something that for transportation monitoring, you would like to be able to do. The flights over people or flights over non-participants, that's been kind of a challenge. The beyond visual line of sight, I would say not so much the nighttime operations, although for some people that's been a restraint. But again, the good news is things are moving in the right direction. Back in April, FAA released new regs that are starting to ease up a bit on some of these things. So I guess in summary, I would say the regulatory side of things does continue to present challenges for the types of things that we'd like to be able to do with UAS in the transportation space. But I see things moving in the right direction.
Thank you.
Great. I apologize. We have hit our hour, so I'm going to conclude with that. Thanks to everyone for joining, and a special thanks to Dr. Parrish for taking the time and the really great and in-depth survey of all of the different things going on with UAS and transportation. So to everyone, have a great day, and thanks for joining.
Thanks everyone for dialing in.
Thanks everyone. Goodbye.
Bye.